So what we're going to do here is we're going to give a proof by contradiction. So how does that go? So proof. Suppose the square root of 2 is a rational number, right? Then there exists p and q in the integers with q not equal to 0, such that what? The square root of 2 is equal to p over q. So, without loss of generality, we may suppose p and q are positive, since the square root of 2 is positive, right? If p and q are both negative, we can cancel the negatives and work with minus p and minus q, right? So there's nothing lost in assuming p and q are positive. You guys see that? If square root of 2 is negative, it could be that the numerator is positive and the denominator is negative, or vice versa, right? But this is the case here. So then what? What is it? What is the square root of 2 defined to be? Then what? So thus, we could say, q times the square root of 2 is equal to p, which tells us what? Q squared times 2 is equal to p squared. Right? Notice both q squared and p squared are formed by prime factorizations with even exponents, right? In particular, two let's see here. Yeah. So, if we look at this, I try to argue this here. If you look at this equation here, let's call it star. Star shows 2 is in the prime factorization of p squared, doesn't it? Anyway, if I can get to the point here, we have p squared has a prime factorization where every prime has an even power, right? So, but 2, so there's two cases, I guess, technically speaking, logically speaking. Either 2 is in the prime factorization of q squared, or 2 is not in the prime factorization of q squared, right? So if 2 is in the prime factorization of q squared, if 2 is a prime in, factorization of q squared, then 2 times q squared has odd power of 2. Because you have 1, 2 here, and you have even numbers of 2's here, right? Which is a contradiction, because p squared has to have an even power of 2. So that's a contradiction, right? On the other hand, if 2 is not, prime factor of q squared, then we also get a contradiction, right? Because then we have 2 is a prime factor on this side, which has multiplicity, the exponent's 1 for this number, but 2 is an even exponent over here. So it's the same contradiction, basically. We have an odd number of powers of 2, we have an even number of powers of 2. Now there's a way to write this more elegantly so you don't do case-wise, you just do it all at once. If you write the sentence right, you can see it all together at once. But this is the proof. So therefore we get a contradiction, which then says that, hence, square root of 2 is not an element of the rational numbers by proof by contradiction. So in your homework, I have given you guys a similar but different problem. In your homework, I've asked you to prove that the square root of 3 is not rational. So you're going to do something very similar to what I just did, except you're going to probably want to focus in on, powers of 3 in the prime factorization, right? So that's it for today.